We're now going to look at the range equation that's going to give us a better idea conceptually of how projectile motion works. And just to tell you, the range equation and this page of notes is not a page of notes I really use to problem solve. So if we are speaking of projectile motion, I will reference the equation down here at the bottom, and we'll talk about how that equation and those variables help us get a better understanding of projectile motion. But to problem solve, I really advise you, and myself will problem solve using separate x and y direction analysis like we have just done. But it is very instructive to consider this situation. So special case, range equation, delta y equals 0 only. Please only ever apply the range equation to this case. So if the projectile does not make it back to the ground, range equation doesn't apply. If the projectile goes past ground level, like shot from a cliff, range equation does not apply. So please do not ever use the range equation if it is not a delta y equals 0 problem. And let's see how this plays out. Well, we have our initial velocity that the projectile is leaving the barrel with. We know we have v initial cosine theta for the x direction. We have v initial sine theta in the y direction. And let's take a look at what our constant acceleration equations give us. So first in the y direction, since delta y equals 0, v final equals 0, v initial equals 0, so we get 0 on the left-hand side. I went right to the v initial in the y direction equals v initial sine theta, so you might want to put that in above just to remind yourself that's where that came from. Minus 1/2 gt squared. G. Well, the acceleration due to gravity for projectile motion is always negative 9.8. Now I'm replacing the 9.8 with a g, so you'll see why when we get to our result. But please do not ever double dip. G is always positive 9.8. The negative here goes with the negative here. So I don't want to put in another negative for G. So G is the magnitude, just 9.8. Well, you can see how the algebra works out then, and that's why I have it highlighted here. We can take this equation. We have our zeros in here, and we have a t at this spot and a t squared here. So all I did was factor out the t and then bracketed in the rest of the variables. And you can see that this equality is solved with one of two situations. Either t itself is 0, and that is correct. The y position equals 0 at time t equals 0. And the bracketed term, or the bracketed term equals 0, right? So, and that's the more interesting one because that's the referring to the final time over here. So we let the bracketed term equal 0, we solve it for t, and that's where this equation comes from. So just the bracketed term said equal to 0, I solve it for t, 2v initial sine theta over g. Well, let's take a look at the x direction. In the x direction, we only have the one equation to work with. So x final equals x initial plus v initial in the x direction times time. So this is v initial in the x direction. You can get that in there to remind you. X initial is 0 because we're starting at 0, 0, the origin. And all I have done here is substitute in for t. So I took the t value here. I substituted it in here. And that's my highlighted term that I have. The 2v initial sine theta over g is in for the t. And now we are done with the one exception of having the very insightful result that 2 cosine theta, sine theta, fits our double angle formula from trigonometry, sine 2 theta. So we get the range, right? X final is the distance that it goes. I'm plugging in r for x final now, the range. The range equals the initial speed squared times sine 2 theta over g, And this equation is very helpful in helping us understand what makes a perfect projectile when an object is fired from ground level to ground level. Well, if you really want that projectile to go far, which oftentimes we do, whether it's a golf ball or a football or a cannonball, oftentimes the object is to make it go really far. So if you want to build a really powerful cannon, right, to be able to shoot the bad guys at a far distance, then you want a cannon that fires a really fast cannonball, right? You want the initial to be big, and that's good, right? So if the initial is big, that's good. You have a strong cannon, but it's not just good, it's good squared. It's the initial squared. So if I have a cannon that fires at speed v, and your cannon fires twice as fast, your cannonball is going to go 4 times as far as mine because it's v squared. Well, we want to maximize this bracketed term, sine 2 theta as well. Sine is a maximum at 90 degrees, so we want the 2 theta to equal 90 degrees, which means theta needs to be equal to 45 to maximize the R position. And the last thing, ideally, I guess we would want to be able to have a magical power to reduce the gravitational acceleration g. Usually that's fixed. Sometimes on multiple choice questions or on a test, they'll ask you to compare a cannon here on Earth to a cannon on the moon. Well, the moon has a gravitational value that is about 1/6 the Earth's gravity, so your moon cannon would go 6 times further. So if they're going to change g on you, smaller g value lets it go further, and that makes sense, I hope, because gravity is going to bring that cannonball back down to the ground. The stronger it is, it's going to bring it back down to the ground faster, and the weaker it is, it's going to let it stay up in the air longer. So there you have it, and my advice is to let your basic problem-solving mindset be to, again, just use the constant acceleration equations and separate it into x's and y's. However, if you do have this 0 to 0 to work with, you can use v initial squared sine 2 theta over g. And let me erase my ink here to use, but please only use it from ground level to ground level to answer these types of questions over here. Okay, and we will move on.